Okay, so like George was mentioning, welcome everybody. We're Tech Sales. We are the manufacturer's rep for EA Technologies. We cover 6 states, as you can see on your screen. Primarily, most of our facilities and people are located in the Texas market. Houston, Texas is where our warehouse is. We have 27 people covering the 6 states that you can see. Most of our products are really around control panel components. So electrical or automation controls is what we specialize in. Everything from the enclosures to power quality, which we're going to be talking about EA today, as well as hazardous locations or commercial construction. Some of the manufacturers on the enclosure side are, as you can see here, steel enclosures with Hammond, Attabox with non-metallic, and Abtech for our hazardous location enclosures. Construction products, we stock transformers, dry type transformers in our Texas facility. We also have strut, cable tray, cable ties, and also aluminum cable for commercial construction market. A big area for us is lighting. So any type of commercial or industrial lighting we can help you out with as well. Just let us know what you need and we'll help you find the right product for it. Power quality and site reliability is a big piece of our business. So we have everything from harmonics to ground fault protection, UPSs, either single phase or 3-phase UPSs, and then oil type transformers as well. Then we have the automation and motor control with drives, circuit breakers from LS, hazardous location products like barriers, isolators with MTL, smart breakers, fender relays. So again, more components inside of an electrical panel, as well as switch gear through the Myers group. Finally, industrial wire and cable. So anything from power cable to instrumentation cable. We also represent manufacturers for European cables like the BATS, LAP, Saab, Helicable, Electrotech. Cable is who we represent there, as well as some fittings, specialty fittings and glands with a couple of our manufacturers. So that's a quick rundown. So George, you can take over from here.
Yep, sounds good. All right, so you should see my screen again.
Yep.
Okay, all right. Again, thank you everybody for your time today. Just a couple housekeeping things. We will be recording the webinar and email you a copy. It'll also be posted on Tech Sales YouTube channel. If you have any questions, use the chat box to ask them. If they're, I noticed in the registration there's some existing users of our equipment. If you have a real technical question, certainly you can ask it. We'll probably come back to you offline. We get a copy of all of the questions. Since this is just going to be an introductory webinar, but there's certainly going to be some things for you to learn as we got a lot of examples and case studies here. So let me get started. Just one slide about our company. EA Technology was part of the regulated utility in the UK. Then when deregulation came, EA was spun off. As the research arm, we not only make instruments, we also do consulting for asset management. We have software for asset management. We also have a electrical forensic laboratory for failed components or equipment that you could send to the lab to get at the root cause. We also do some field service work. All of that is experience is built into some of the instruments that you're going to learn about today. And we also are global. We have offices around the world. So what is partial discharge, and why do we care? This section here. Partial discharge, first part of the answer is where can it occur? And in that first bullet, the key point is 3.3 kV or medium voltage. 769 kV is just the highest we've ever seen, but it really has no limit. You can have partial discharge on low voltage, so if you had a 480 volt equipment or circuit. However, the insulation typically in those low voltage components are going to be so oversized that it may take a lifetime for the partial discharge to cause a failure. You'll have a failure for other reasons long before PD. And then the rest of the bullets are just different places in a facility that you might have, you know, switchgear cubicles, outdoor, indoor insulators. Yeah, you could read the list there. There's quite a number of places. Anywhere that you can have medium and high voltage is the main takeaway here. So let's get into some examples. It's always a great way to learn. This is a little clip here. You may not be able to hear the sound, but it's visible discharge that you see there. The link down below, we're going to email you that link tomorrow, along with a copy of the webinar. It's a short video that we have on YouTube, maybe 5 or 8 minutes, with a ton more of examples and all the audio. There's really no talking or sales pitch in that video. So you could just kind of calibrate your ear to the different sounds of PD versus noise. So here's another example. This is a surface partial discharge, and going through the examples, just make some mental notes on these examples, and we're going to refer back to them as we go into the theory a little bit more. So here you have surface partial discharge, and the technique used was ultrasonics. And you could see this white powder, which is the insulation there. That's a classic sign of PD, and it's due to the lack of stress control for the electric field on that one. Here's another example I'll spend a little time with. Again, it's surface partial discharge, and it was detected with ultrasonics. So this, on the left, there's a door that was here, bolted down, and with the ultrasonic sensor, we were able to detect a lot of PD activity there. And as you can see, this in the close-up on the right, there is a classic tracking. This boot just phase to phase was too close, and you could see the white powder and the tracking. This is classic signs of PD. The other interesting thing about this is all that rust that you see at the top of the panel. If you notice at the bottom of the panel, there's no rust. These bolts that are down here, the tray that's down there, nothing's rusted. So you would think if there was water ingress, it would be at the bottom, it would collect and pool, and you would have rust there, but instead you have it up here. The reason it's up here is because partial discharge gives off some gases that are corrosive, and when you see rust in places that you wouldn't normally think that there's rust or bolts or in this case the metal back here, that could be a sign of PD. And we'll talk about what these gases are in a future slide here. Here's another example. Here you have surface PD again. When the door was closed, it detected the noise by ultrasonics. This horizontal insulator here is supposed to hold the bus bar in place, but it accumulated a lot of dirt. The dirt, this is a high humidity part of the country. the humidity created the dirt, and everything started to become conductive, and then you could see the partial discharge in these close-up photos. So basic lack of maintenance, lack of cleaning led to this problem. Here's a different example, again, surface partial discharge with ultrasonics. So the horizontal insulator, you would think it'd be fine to have these unshielded cables resting on. However, even after having the contractor, an engineer from the factory, and the customer all sign off on this, they ended up with partial discharge. That sharp edge that you see there is not good. It affected the electric field and the stress control, and then you could see here in the left on the right hand side the final effect of these cables. Here's a different example, unshielded cables again, lack of stress control. These phase to phase were too close to each other, and you see the evidence of that are circled here of white powder and tracking. Here's an example of internal partial discharge. This is a cast resin current transformer, and in the resin started out as a small void, and once you have partial discharge, it always will increase. You can try to minimize surface PD, but it will it doesn't go away, and eventually it led to flash over and a failure. Internal partial discharge, we'll talk about detection techniques in upcoming slides here. Here's another example. This is in a Caribbean utility, so a lot of high salt air and humidity. This equipment is supposed to last dozens of years. The average life is maybe 6 years. You could see the metal is corroded, the tracking on the insulator, everything is classic examples of PD here. Here's another example, two types of PD in this example. It's an outdoor, as you can see. You have internal and surface partial discharge. So the internal partial discharge was detected with a technique called TEV, transient earth voltage, which we'll talk about in the upcoming slides. And there's also surface activity, and that's the graph that you see here. It's an output out of one of our instruments. You could see two groupings here, very simple to detect that you have surface partial discharge. And we'll talk about these, briefly talk about how to interpret these. Here's a different example of surface partial discharge. This one was detected using UHF or radio signal. We have a UHF antenna that can be used for that purpose. And you can see again two groupings here. With radio, you can detect internal and surface partial discharge, but in this case, with the TEV technique, you couldn't get up close to do the technique. So using the UHF is preferred. So those are some examples, and let's talk about just one slide here, a couple slides on the theory. So when you have an insulator represented in this little diagram here, we're showing a void inside the insulator. You have the conductor and the ground on the opposite ends. The void could also be on the surface. The point is, though, that you have an air gap. And if you remember the first example that I gave you where it was charging and discharging, that's what's going to happen. The air is still acting as an insulator, but at a certain point, it's going to be overcome, and then you have a discharge across the insulator, across the void, excuse me. And that's what's being depicted here in this example. Now, different manufacturers, or if you look them up on the internet, you may have different nomenclature as far as the types of PD. This is how we've classified them. So if you're having a conversation with us, this is the terminology that we'd be using. So the first type that's shown here is corona discharge. Oftentimes people confuse all types of PD as corona, and that's not the case. Corona is a specific type of partial discharge. It occurs typically, as you can see in the little diagram here, off of sharp edges. You're going to typically see it outdoors in your maybe a bolt or a bracket or something that's in the presence of the electric field. It's not typically a problem unless perhaps the corona occurred inside an enclosed area where the gases accumulated and became corrosive. Techniques to detect corona, you have radio via VHF, ultrasonics, UV light cameras or corona cameras. By far the most common type of partial discharge is surface PD. So in this example, if you look at that little diagram, you'll have tracking the examples that I showed you. It's pictures along the surface of a cable. It could be a type of insulator. And the techniques are going to be ultrasonics. You could use UHF and corona cameras. The next type is called internal partial discharge. So that's the example of that CT that I showed you earlier with the void inside the CT. These cannot be detected with ultrasonics, just no path for the sound. You're going to use the technique that we're going to talk about later, TEV. You can also use UHF. Internal partial discharge and surface PD, they emit in a wide band in the radio area, so you can use UHF for both. The final one is we call contact discharge. Some people call it floating metal. So in that situation, its best example is someone leaving a bucket of tools inside a switchgear cabinet. I mean, that's a classic textbook type of case of floating metal. Other examples could be a loose bolt or rusted ground. Those are some examples of contact discharge. So let's talk about some of the causes of PD. We kind of covered them in the examples, but here they are in bullet form. You have surface contamination, lack of cleaning. Remember that example I talked about earlier where there was the bar and you got dirt, and with humidity becomes a problem. You have workmanship issues. You know, in the manufacturer, you can have manufacturing defects, but typically you're going to have more workmanship issues in the field. You know, in a manufacturer of equipment or cables, they're going to be in a controlled environment. But once you get them out into the field, you know, you can have all kinds of weather and other contamination issues, or the amount of training of people, or the quality of the parts that they use, or the using the wrong parts. If you live near an ocean, you're going to have, you know, salt and humidity related to that salt air. Certainly age could be a problem. So you have a basic list here of different things that might cause partial discharge. So now I'm switching gears, just put the hat on that as if you're going to design an instrument to detect partial discharge. And so in this chart, let's talk about what are the symptoms, or how can what are we going to measure in order to detect partial discharge. So some things like the light emission, you know, they're helpful, but to design an instrument around that is going to be difficult. Sometimes you can hear partial discharge in the audio band, but by then it's going to be pretty late. You have the ozone. You might be in a switchgear room and you smell ozone. And then you have these, you know, the current pulses that you might have. But to make an instrument from these is going to be difficult. Then you have characteristics that could be particularly dangerous. You have the heat. It could lead to insulation damage. The ozone can become nitrous oxide. Again, with the nitrous oxide and humidity, you're going to create nitric acid, all bad things. But to design an instrument, we have the useful row here. So you have RFI, radio frequency interference. So that's the UHF, VHF. Here's a picture of one of our instruments, the UltraTev Plus 2, with an accessory for a UHF directional antenna. Then you also have ultrasonics, which is the most common technique. Here's a picture of our UltraTev Plus 2 with a complete kit of different ultrasonic sensors. And then that includes a TEV sensor for internal partial discharge and a sensor for cable partial discharge. And we'll kind of cover these techniques in the upcoming slides. So just a quick comment about non-invasive versus invasive testing. Our company, EA Technology, is focused on non-invasive techniques, online detection. There are plenty of companies that make offline tests. So in these offline tests, you would remove the cable or the equipment out of service. It would disconnect it and run your tests. The goal with our company is to narrow down, 100 different areas in an online non-invasive way, so that you can narrow down to the ones that you're going to do maybe a visual inspection, or if you want to do an offline test. So as far as actual testing techniques in the online non-invasive methods, so we have just to bullet some of the points that we covered so far. So you have ultrasonic or acoustic testing, and so you're going to look for openings like louvers or vents, areas where there's a path for the ultrasonic sound to get to the sensor. There's the TEV sensor, which is the transient earth voltage, and it's used to detect internal partial discharge. And then we have a current transformer. Some people call it RFCT for radio frequency, or HF for high frequency. By attaching these to the ground straps of cables, we can do cable testing. And then there's the RF testing with the UHF antenna that I showed you a picture of before. So those are the basic techniques that are used for non-invasive testing. So let's talk about these techniques next. So here's ultrasonic. Here you could see a technician. He's got his headset on so he can hear. The ultrasonic partial discharge with a math algorithm is brought down into the audio range by the instruments, and that way you can hear the PD. And then you are looking for any gaps between the doors, any louvers, if there's a missing screw or bolt. There are ultrasonic windows that are available in the marketplace that you can install as well. But you're basically looking for sound when you're dealing with a switchgear cubicle. And meanwhile, at least with our instrument, there's a graph and information being displayed in the handheld. So you want to look at that while you're checking for PD. Some practical considerations. You have the environmental aspect, temperature and humidity. So you want to pick days that are high humidity to do your testing, not raining, because then you'll have the sound of the raindrops is going to potentially mess up your readings. If you're testing once a year, you want to test on the, in the summer and the high humidity day. If you're testing twice a year, maybe you want to do spring and fall. That way they're comparable. Or if you're doing monthly, you certainly want to have an instrument that's going to record the humidity and temperature so you can compare results. And you're going to be listening for with your headset, a distinctive crackling noise. Some people call it similar to bacon frying, and it's going to have a 60 or 120 hertz component to it. This last bullet I just want to spend a minute on. The severity of discharge is not necessarily related to noise amplitude. So what that means is the instrument is recording decibels. However, if you're dealing with like a switchgear cabinet, it's comparable to me talking at a certain decibel level and then putting my hand over my mouth. I'm still talking at the same decibel level, but when I cover my mouth, obviously you're not going to be able to hear it in the same volume. And so relying just on decibel, older instruments, maybe 10 or 15 years ago, all you had was the decibels. And if you're just taking notes of decibels, it may hide a low decibel number may hide a real problem if it's muffled by the switchgear panel. So just something to take into consideration. And that's why our instruments have evolved from that to give you some additional information so you can make a decision. Speaking of decibels, this is the interpretation chart. Obviously, if you have anything above 11 dB, you're going to have, it needs investigation right away. But again, below that, like in that 7 to 10 range, it's hard to know if it's muffled or not. This table is used by originated from our experience, and then some of our competitors are using it, and it is now incorporated into a NETA standard as for doing partial discharge testing with ultrasonics. So let's talk about TEV, or internal partial discharge testing. So there's a phenomena that occurs with an internal partial discharge where you get a high frequency current pulse. It rides along the metal looking for a path to ground. Sometimes they call it the skin effect. And so if you put a particular probe like our equipment has, a capacitive plate against the metal, we can detect that current pulse and determine, if you have partial discharge. Now, this high frequency pulse that's going through the outside of your switchgear panel or this bus duct, it's not harmful to the touch, but our the instruments will be able to detect it. You would not only use it here, you'd use it on test it on switchgear panels. Here's an example in an outdoor situation. You could, if you have outdoor ground cables, you could check them. Anywhere you have metal, you could check for TEV. Like ultrasonics, TEV has its own interpretation chart. The decibel range part, the x-axis here, is also incorporated into the NETA standard, but we've also added this other column, the y-axis, pulses per second. So one of the things that with TEV is we also monitor how many pulses per second that you have. If you have way too many pulses per second, so in this graph you have a scale of like 1,000, you could see it's probable background noise. There could be some motor or some other outside interference. in a certain range, as you can see here in the pink, you have possible surface partial discharge. In the case of our instrument, the algorithm will tell you that you have possible surface PD, and it'll recommend that you switch sensors. But the sweet spot for internal PD is, as you can see here, in the range of dB 10 to 50, and then pulses per second, maybe half a pulse to 6 pulses per second, somewhere around that range. So just to sum up internal versus external, internal PD, because it's internal, it's not going to be affected by humidity, whereas external PD, surface PD, you will. The pulses per cycle will vary between the two. The audible range and the ultrasonic range is going to be in the external or surface PD. It's the one that you're going to be using. Internal PD, you're going to use TEV. Also, you could use UHF if you're working outdoors. Another area is cable partial discharge. Based on our forensic lab experience, the most common place of cable PD is going to be at the cable terminations in the stress relief, trying to get these equal potential lines to relieve the stress. Detection technique for cable PD, we'll talk about in a second. First, let me give you this example of a horror story here. You can see that this is a cable termination where they cut back the insulation and they left this sharp edge that's circled here. That sharp edge created partial discharge, and you get tracking in both directions and eventually a flashover. So the actual technique, whether it's on the surface or internal, a current pulse, high frequency current pulse is also going to be generated, similar to TEV, and it's going to run down the ground strap. And so if we put a sensor on the ground strap, a high frequency current CT, a split core CT, will be able to detect it. And in certain situations, based on the initial and reflected pulses, we may be able to detect the distance to the point of where you have PD. So in this section, I'm just going to talk about instruments. I want to keep the conversation general as far as generic, but we're going to use our UltraTev Plus 2 as the example instrument here as far as the types of features that you're going to want if you're selecting an instrument for measuring online PD. So in the case of our instrument, the UltraTev Plus 2, it's a fourth generation instrument. We have a touchscreen, we have a number of accessories, sensors that are available with it. The instrument does not need any special software for your computer. Everything's stored in HTML and it can be exported to a CSV file. It has USB, it has Wi-Fi as a hotspot, it can connect to your networks, and it has a memory card, so a number of different ways to get the data out of the instrument. Here's a couple of examples. We feel that it's important not only to have your headset on and have a dB value when you're looking at the display, but also have some graphs and some information. And we also have an algorithm to help you along with your PD surveys. So in the top example here, you could see it's logging the temperature and humidity. The Wi-Fi is enabled. It's also measuring the frequency of the process that you have there. You have 29 dB, it's in the red, it seems like it's an alarm, but if you look at the pulses per cycle, it's 28 pulses per cycle, which is very high. So the instrument algorithm is recommending that you switch to the ultrasonic sensor, that it's not going to be TEV or internal PD. Here's a different example. Here the algorithm is telling you that you have PD, you have 17 dB, much lower than 29, but still in the red. And then you also have a quick graph here, and you can see two groupings of samples. And let me talk about that a little bit. So with PD, you're going to have, you know, on the sine wave, it's going to happen on the rise, whether it's on the positive or on the negative side. That's where you're going to have the partial discharge. What we've done in the graphs that you see, whether it's on the instrument or in the HTML file that you use your web browser for, we've laid them flat. And although you see a graph here from 0 to 360, we're not connected to your network, so we don't know the exact phase. It's just a representative to show you that you have two groupings 180 degrees apart. You don't have to get any more complicated than that, reading complicated oscilloscope graphs and so on. It's pretty straightforward. Here's an example for Corona. The acronym there, PRPD, it just means phase resolved partial discharge plot. This is the output that you get in HTML, so you would open up any your default web browser. You can see only one grouping in this case. So with Corona, that's what you're going to see in the case of Corona. It's going to just discharge to air. Let's talk about TEV. TEV measurements in our instrument. We have that capacitive plate that I showed you in the examples earlier. It's on the front of the instrument. You just put it up against the metal switchgear panel or any other metal that you want to check. And while you're watching the display, waiting for the reading to settle. Typically, if you're going to set up a survey, you're going to want to take the readings in the same spot. You maybe have a sticker in that spot or a mark of some sort. With TEV, like with ultrasonics, there's an interpretation mode. This left example we showed you earlier, 29 dB, the instrument's telling you that you want to switch to surface or ultrasonics. The middle example is true internal PD. So you have 32 dB, the pulses per cycle is 0.87. It's in that sweet spot range, definitely something to investigate. Then on the far right here, you have 23 dB. It's still a high dB, but the pulses per cycle is 85. It's very, very high. It's going to be some noise. With TEV, like with ultrasonics, there is a phase resolved plot. Here's an example. There are some additional screens. I know there's a lot of information here. You're going to get a copy of the presentation, so you can read all of that later. In the interest of time, I'm just going to mention that we have this histogram screen. We also have a waveform screen. These are additional screens to help you investigate TEV problems. Just something I forgot to mention earlier, in the scheme of things, of all types of PD, if you had a pie chart, internal PD is going to be a small subset of that. I don't have any statistics on that, but let's say 1%, 5%, something like that is going to be internal PD as opposed to surface PD, which is going to be the most common, or Corona. Those are the ones that you're going to find more commonly. So these additional screens are really you're going to use, in advance, should you come up with a situation like that. So to do the ultrasonic measurements, in our instrument, we have 4 different types of ultrasonic sensors. You have a sensor built into the front of the unit. You have the flexible sensor, which makes it convenient so that you could look at the display while you're working, or if you have to work overhead, or where you don't have to kneel down if you're working down at a lower height. There's also the ultra dish. It's a parabolic dish that concentrates the ultrasonic signal. This is going to be great for outdoor applications. There's also a contact sensor, and I'll explain its use here. Just notice that these little circles around the center is where the ultrasonic sensor is. These little circles around the outside are magnets, so this is a magnetic contact sensor. And I'll discuss that one here in a few slides. So again, when you're doing ultrasonics, you're going to want to connect your sensor, select the right sensor for the application. You're going to watch the screen. You're going to listen as well, and make sure that you take your time. Like in this example here, there's no electrical equipment behind it, but should there be, you may want to move positions because the dish might be picking up something behind, so you just change your orientation. In our particular ultrasonic parabolic dish, there's a laser sight as well as a gun sight that you could use to align to what you're looking for. I would recommend, if you're doing any work outdoors, that you get a good pair of binoculars, a 10x, even just a compact 10x binocular. So if you find something, maybe it's a dirty insulator or something, you can just take a look at it while you're working there. So I mentioned the contact ultrasonic sensor. This is the application here where where you would use the wand, the flexible, and then you have plenty of an air path inside a switchgear panel. You're going to look for a missing screw or ultrasonic window or louvers, or you're going to find for air gaps along the doors. But in the situation where you can't, that's where the ultrasonic sensor, that's the contact probe, comes in handy. So you connect it. It's got a metallic magnetic front. The reason we don't depend on this one first is because in this example, you have PD occurring inside this blue box, but so it'll vibrate the metal panel and you'll be able to detect it with the contact probe. However, it could easily be coming from behind you, hitting from the outside if you had some equipment. So the contact sensor is non-directional, whereas all the other ultrasonic sensors are directional. So you would use this one only in the situation where you have no air path. So here's just a review again. You have two groupings. You're going to be looking at the screen. You're going to be looking for the instrument. In our case, has alarm settings all programmed in, so you'll know, in a stoplight fashion, red, green, yellow, where you are. You have an algorithm here, and then if you find something interesting like this, you could record it and have it record an audio clip in a WAV file, as well as the graph. So with the algorithm, here's an example where you have noise. So you have 23 dB, seems high, but if you look at the graph, you have no visible pattern. The algorithm is telling you noise versus the other example where you had 17 dB and clear groupings there, 180 degrees apart. So while you're working in the field, it's nice to be able to get all of that information right there live. And then you can always get some proper recording that you can look at later or have a manager look at as well. But at least you know where you stand as you're doing your surveys. Here's an example of a surface PD. In this case, it was in the audio band. You could hear it with just your ear. It's basically the stress control again is the issue, and here's the output from the recording that you would get in the HTML web file. And you would input, some basic information. In our instrument, there's also, if you connect the hotspot to your phone, you can attach a picture. That's really helpful for a service company that's, at a different job site every day. You can attach a picture. Give you another example here using the parabolic dish. This door was closed, and using the wand or the flexible probe, we could determine that there's a lot of surface PD problems in here, and couldn't take it out of service to inspect. So they opened the door with PPE on, and without having to stick the wand in there, we just used the parabolic dish from a distance. And in the right hand here, you could see the little red dot. That is the laser pointer, and you could see the white powder there. Afterwards, we found out that the cable was cut a little bit short, and it was forced in there, and this boot was bent, and that created a PD. Once the cable was replaced and everything was back up and running, we came back, and there's no evidence of PD at that point. And then, so we covered TEV, ultrasonics with the instrument, doing cable PD. You would use an RFCT or HFCT, so it's a split core, and that connects to the instrument. A lot of the screens are similar to the TEV screens. We are reading in picocoulombs as opposed to dB, so we are getting a measurement. Now, when you install these CTs, you have to follow safety protocols if you're trying to do it in a live environment. To help with that, we offer a hot stick RFCT that you could rent or purchase to at least do it from a safer distance. It won't mitigate all of the risks, but at least some. You also can purchase these CTs and leave them permanently installed. There's some that are outdoor weatherproof rated as well. If you're doing only cable testing, we do offer a cable data collector, which is a dedicated instrument just for cable PD testing, and it could do all 3 phases at once. So last section here, and we'll get into the Q&A, is doing UHF measurements. So here's a picture of the accessory for the UltraTev. It's a UHF directional antenna. One of the nice things about it is you could do it from outside the fence line. Just years ago, people used to wear or bring an AM radio if they were out in an outdoor switch yard, just as a safety precaution, to see if they see the radio signal noise that might indicate a problem. Here is a more modern instrument. It has all of the features of the graphing and the algorithm and so on. It ignores coronas. Remember, we talked about that corona is not harmful per se. Maybe the ham radio guys in your neighborhood would be upset, but it won't necessarily create harmful PD. There's also a shorter antenna that's available for close-up work, although 95% of your applications are going to be with this directional antenna that you see pictured here. So talked about ignoring corona, and so here's an example. This is a corona camera picture of a corona source that we created artificially that we could turn on and off. On the left here, there's a graph with the red and the blue. The blue background is just the background noise with the corona source turned off. Then the red is with the corona source turned on. And then the graph on the right is the difference between the two. So when you look at this area that's circled, there's a certain bandwidth range where corona occurs. So it's going to be, I don't know, let's say 150 or to 250, something like that. It's a very narrow range. Partial discharge, whether internal or surface, when it in the radio band, it occurs in a very wide range, in a wide band. So our instrument you could scan a wide range and focus on another area of the band. We find internationally that 800 megahertz is a good starting point. Here in the US, for example, the FCC kind of has designated that for first responders. So it may be in your neighborhood, it might be 805 or whatever, but around 800 should be a quiet range. So the instrument will allow you to scan all the frequency, so you'd point it at the ground or point it away from the switch yard and then scan the whole frequency and then focus on an area that's quiet and then go out and do your study. And you can ignore corona and just focus on surface PD. The instrument, the UHF accessory, is helpful. Typically, you're going to just depend on the ultrasonic parabolic dish outdoors. But if you have a lot of corona problems, they may, in the ultrasonic range, they may mask some more serious surface PD problems. So that's one of the reasons you might want to use the UHF. If you're comparing, trying to design an instrument, we could have also made a VHF antenna instead. The problem with VHF, it travels a lot further distances, so you may have outside interference problems. You also, just based on the wavelength, the design of the antenna becomes really big. So this UHF is kind of compromised in terms of which frequency range to build an instrument around. And again, here's the picture of the instrument. Has a perfect range for outdoor switch yards, ignores corona. You can adjust the gain and the frequency center spot that you want to measure. So it's a nice accessory for the Ultratech system. So that kind of covers the presentation that I wanted to include. If you have any questions, please put them in the chat. As while we're waiting, just to get things started, one of the common questions that I get asked is about thermography, and can thermography detect partial discharge? I'll just answer my own question there. Only in a very extreme case. If you're looking at those small pulses that you saw in that first example, those are going to be very hard at a distance to detect, and especially if you have switchgear panels where you don't have line of sight. It's going to be very, very hard. Thermography is better for conditions that are under load. So the higher load, higher amperage, more heat, it's detecting heat. Whereas partial discharge is a voltage event. So we did a study, just as an example, with a university where they had a standby generator and they wanted to test the cables that work with this generator. And what they've done is just to make sure the cables are going to be available when they need them. They have a trickle voltage. They leave them energized with a trickle current going through them, and we were able to do our test because they were energized. So that's just an example. Thermography and PD are complementary. So someone that knows thermography is a level 1 should be able to pick up our equipment very easily. Any other questions, guys?
Well, thank you very much, George.
Yeah, not seeing any questions. I'll wrap it up. If something comes to mind, here's all our contact information. Thank you, Steve and Tech Sales, for all the work you guys do. If they have demo equipment, if you want, and can visit you in person, you could reach out to Steve or myself. Thank you again, everybody.
All right, appreciate it.
Thank you. All right, I'll close it out.
Okay, bye-bye.